Swayam Prabha. Digital India. Educated India.
Next, where new ij is equal to summation nu equal to 1 to 2 alpha I nu into beta nu j, which can be written as alpha I1 into beta 1 j plus alpha I2 into beta 2 j. So, this is the general format of the function. Now, we have the multiplication of the product of the indices. This looks rather complicated, however, it is found on relative simple rules, namely multiplying alpha I j into E I j by summation beta I j into E I j and multiplying out term by term and collecting the terms and using this condition E I j into E k l equal to 0, where j not equal to k, and E I j into E j l equal to E I l, term by term collecting. So, we illustrated the multiplication of this, and then we have values of E11 into E12 equal to E12, whereas E12 into E11 equal to 0. So, R is not commutative, therefore, it is possible that and product of U and V equal to 0 and U not equal to 0 and V not equal to 0. Next, let C be a set of all symbols alpha comma beta, where alpha beta are real numbers. We define alpha beta equal to nu comma delta. This condition is true only if alpha equal to beta and beta equal to delta. So, if C introduce addition and defining x equal to alpha comma beta and y equal to gamma comma delta, then sum them x plus y equal to alpha comma beta plus gamma comma delta, then alpha plus gamma and beta plus delta. So, note that x plus y is again in C. We assert that C is a Abelian group under operation with 0 comma 0, serving as identity element for addition minus alpha comma minus beta as the inverse under addition of alpha comma beta. Note that C is endowed with an addition. In order to make C a ring, we still need to multiplication. We achieve by this by defining x equal to alpha comma beta and y equal to gamma comma delta in C. Therefore, x dot y equal to alpha beta into gamma delta, which is equal to alpha gamma minus beta delta into alpha delta plus beta gamma. So, note that x dot y equal to y dot x, also x into y comma 1 comma 0 equal to 1 comma 0 into x equal to x. So, that 1 comma 0 is a unit element for C. Again we notice that x dot y equal to C. So, x equal to alpha beta, which is not equal to 0, then alpha beta is a real and not both 0, implies alpha square plus beta square not equal to 0. Therefore, y equal to alpha by alpha square plus beta square minus beta by alpha square plus beta square. So, this way we can define the part of numbers in complex, and then we can define the corresponding values. So, finally, we see that in a real part of alpha by alpha square plus beta square, imaginary part minus beta by alpha square plus beta square, and we can equate them 1 comma 0, so that it forms a field. So, if you write alpha comma beta as alpha plus beta I, so we can verify the readers, that is follow here. C is merely distinguished form of the familiar complex numbers. So, finite field of the form is GF of 2 power n. A polynomial f of x over a field f is called irreducible if and only if f of x cannot be expressed as product of two polynomials both over f and both of degree lower than that of f of x. Therefore, by analogy of the two integers, it reduced to polynomial is also called a prime polynomial. So, this is the idea we are going to do in cryptograph. So, the polynomial f of x equal to x power 4 plus 1 over g f of 2 is irreducible, because you take x power 4 plus 1 can be product of x plus 1 into this. So, the polynomial f of x equal to x power 4 plus 1 over g f of 2 is reducible, because x power 4 can be product of the two factor x plus 1 into x cube plus x square plus x plus 1. Consider the polynomial f of x equal to x cube plus x plus 1. It is clear by inspection that x is not a factor of f of x, and we easily shown that x plus 1 is not a factor of f of x. For example, you take x cube plus x plus 1, it divided by x plus 1. So, x into x square is x cube, and then x into 1 is x, and here we have what 1 into x is x square, x square into x is x square, therefore, and then subtract them. So, it becomes cancelled, and then x square plus x, and then once again you multiply with 1 x square plus x, then the remainder is 1. Therefore, f of x has no factors of degree 1, but it is clear the inspection that f of x is reducible. It must have one factor of degree 2 and one factor of degree 1, therefore, f of x is irreducible. So, this way we can say that the polynomial is reducible, irreducible, like that. So, for addition, if you do that, if polynomial of degree 7, right, x power 7 plus x power 5 plus x power 4 x cube plus x plus 1, if you add them, then we have what x power 7 plus x power 5 plus x power 4, corresponding this term will come, and then rest of them is subtracted, it becomes what 0, because x cube plus x cube resultant is 0, like that. Because 1 plus 1 is a 2, under modulo 2 it becomes 0, therefore, we have to take it out. For the subtraction, do like that, and then simply cancel this part, or that is all. For multiplication, first you have to multiply with x 1, therefore, first term will come, and then second you multiply with the x, so that x into 1 is x, x into x is x square, x into x cube is x power 4, x into x power 4 is x power 5, x into x power 5 is x power 6, x into x power 7 is x power 8, and then multiply with x cube. We have 1 into x cube is x cube, 1 into x is x cube is x power 4, and x cube into x cube is x power 6, x cube into x power 5 is what x power 8, x cube into x power 4 is x power 7, x cube into x power 10. Now, we have to what add corresponding 1 plus 1, 1 is 1, x plus 1 is say under modulo 2 is it becomes 0. So, here 0, and then x square, and then it becomes 0, and then 1 plus 1 plus 1, therefore, 1 x power 4, here it becomes 0, here it becomes 0, 0, 0, and then here this. So, after multiplication, they simplified, the value is only x power 10 plus x power 4 plus x square plus x plus 1. So, this way we can do for polynomial under modulo of GF of 2 power 2. Similarly, if divide x power 7 x power 5 plus x power 4 plus x cube plus x plus 1 by x cube plus x plus 1, and then you have a division algorithm that x power 4 first to multiply x power 7 will come, x power 5 will come, x power 4 will come, then it becomes 0, it becomes 0, it becomes 0, it means cancel, and then we have x cube x plus 1 and multiply them with 1, then it becomes 0. So, it pakka divides, therefore, it is a factor, therefore, it is reducible. So, like that we can do with Galois field, then it is very helpful to in cryptograph elliptic curve and super elliptic curve and hyper elliptic curve and so on. Now, we have a division, find the greatest common divisor. We can extend the analogy between the polynomial arithmetic over a field and integer arithmetic by defining the greatest common divisor as follows. The polynomial C of x is said to be a greatest common divisor of A of x into B of x. Then C of x divides both A of x and B of x. Any divisor of A of x and B of x is a divisor of C of x. Therefore, the GCD of A of x comma B of x is the GCD of B of x comma A of x into under modulo of B of x is a extended Euclidean division algorithm ideas. Now, Euclidean algorithm for polynomial, we have to calculate Rn of x, that is divide one number by another number and then with the help of divisional algorithm A of x equal to quotient into divisor plus remainder, and then the A of x is identically equal to R1 of x under modulo of B of x. Similarly, compare with B of x and R1 of x, B of x is greater than R1 of x and divide them, then the new quotient Q2 into R1 of x plus R2 of x, and obviously B of x is identically equal to R of x under modulo R1 of x. Similarly, you have compare with R1 and R2. R1 is greater than R2, then R1 of x equal to Q3 of x into R2 of x plus R3 of x. Therefore, R3 of x is identically equal to R1 of x under modulo R2. Proceeding in this way, we have the sequence that is R suffix n minus 2 x divided by R suffix n minus 1. Therefore, we have R suffix n minus 2 into quotient into R suffix n minus 1 plus R1 of x. So, obviously, R suffix n minus 2 of x is identically equal to R1 of x under modulo of R suffix n minus 1 x. Therefore, we can write R suffix n plus 1 of x equal to R suffix n minus 1 of x under modulo of Rn of x equal to 0. Therefore, R suffix n minus 1 of x equal to Q suffix n plus 1 of x into Rn of x plus 0. Therefore, d of x equal to the GCD of A of x comma B of x, which is equal to Rn of x. So, at each iteration we have d of x equal to the GCD of R suffix I plus 1 of x into R suffix I of x until finally d of x equal to greatest common divisor of Rn of x comma 0 equal to Rn of x. Thus, we find the greatest common divisor of two integer by repetitive application according to the division algorithm. This Euclidean division algorithm for polynomials assume that the degree of A of x is greater than the degree of B of x. Now, find the greatest common divisor of A of x comma B of x for A of x equal to the 6th degree polynomial like x power 6, x power 5 and so on 1, and B of x is equal to x power 4 plus x square plus x plus 1, divide one by the other, that is A of x by B of x. Therefore, x power 6 plus x power 5 plus x power 4 like that divided by this term, and first the possibilities is x square you take it, therefore x power 6 into x power 4, x square into x square, x square into x, and then x into 1, x into x, x square, sorry, x square into 1 is x square, and then subtract them. Therefore, cancel, we have only x power 5 and we have to carry this one x plus 1, and next you take x and then multiply with x power 4, x power 5 will come, x into x square is x cube, x into x is x square, x into 1 is x, then subtract them, it becomes what 0 here x cube plus x square plus 1. Therefore, Rn of x is x cube plus x square plus 1 and Qn of x is x square plus x. And now, we divide B of x by Rn of x, we have what x power 4 plus x square plus x plus 1, and we have what divided by x cube plus x square plus 1, then multiply with x, x power 4 x square into x is x cube, x into 1 is x, then subtract them, and then we have x cube plus x square plus 1, and then once again multiply with 1 x cube plus x square plus 1. So, that it yields R 2 of x equal to 0 and q 2 of x equal to x plus 1. Therefore, the GCD of a of x comma b of x equal to R n of x equal to x cube plus x square plus 1. So, this way we can do for finding the greatest common divisor of this number. Consider a set of all polynomials of degree n minus 1 or less over the field of integer modulo p. Thus, each polynomial of the form the a suffix n minus 1 into x power n minus 1 plus a suffix n minus 2 into x power n minus 2 and so on, a 1 of x plus a naught equal to summation I equal to 0 to n minus 1 a I into x I. So, we have a table that is arithmetic in GF of Galois field of 2 cube is 8 that is 3 bit. Therefore, you have a 0 0 corresponding value of 0 is 0, here is 1, here is 2, 3, 4, 5, 6, 7 corresponding to bit. Therefore, we can represent like that in a Cayley table. So, ordinary integer modulo 0 you do that. So, that 0 plus 0 is 0, 1, 2, 3 and so on 7 like that, and then 1 plus 1 is 2 under modulo 2 is 0, 1 plus 2 is 3, right, and 3 plus 1 is 4 under modulo 2 remainder is 2, right, like that. So, that is 1 into 3 is 3, then corresponding the value is 2. So, we have what 1 plus 3 is a 4, 4 and then modulo 2 is 2, and then 1 plus 4 is a 5 under modulo 2 is corresponding 5, 4, 7, 6 will come, and similarly we have a what this value it becomes 0 and 1, 6, 7, 4, 5 like that. We can add the Cayley table of the integer modulo using the arithmetic. So, we have what 2, 1, all the values will come, right. So, 2, 1, 0, 1, 7, 6, 5, 4. Similarly, you calculate the rest of the Cayley table of this one. This is called it as arithmetic in Galois field of modulo Galois field of 2 cube, right. Next, for multiplication, so everything multiplies 0, here 1, and then 1 into 1, 1, 2, 3, 4, 5, 6. Similarly, for 2 into 2 is 4, 3 into 2 is 6, and 4 into 2 is 8. Then we have a modulo, it becomes 3, and 5 into 10 and corresponding divide them, and then we have 1, 7, 5 will come. So, similar way we can calculate rest of them. So, divide one another and then the remainder you have to take it. So, that is equivalent to value of this. Similarly, for additive and multiplicative inverses, one having the inverse 1, 2 having the inverse 5, 3 having inverse 6, 4 having 7, 5 having 2, 6 having 3, 7 having 4. So, it use the integer modulo of 0 to p minus 1. There are total of p power n different polynomial in S. Suppose if you take p equal to 3 and n equal to 2, we have 9 polynomials in the set R the corresponding value 0, 1, 2 for 3 x and for 4 x plus 1, for 5 x plus 2, for 6 2 x, and for 7 2x plus 1, for 8 2x plus 2. If p equal to 2 and n equal to 3, then 2 power 3 equal to 8 polynomial in the sets for 0 1 x, then for 3 3x plus 1, for 4 x square, for 5 x square plus 1, for 6 x square plus x, for 7 x square plus x plus 7 x plus 1. So, this way we convert into a polynomial of the residue. So, with the appropriate definition of the arithmetic operation, each such set S is a finite field, and the definition consists of the following elements. That is, arithmetic follows the ordinary rules of polynomial arithmetic using basic rules of algebra. The following refinement, following two refinement, and the second is arithmetic on the coefficient is performed under modulo p, that is, we use the rules of arithmetic for the finite field of Zp. If multiplication result in the polynomial of a degree greater than n minus 1, then the polynomial is reduced to modulo some irreducible polynomial m of x of degree n. So, we divide by m of x and keep the remainder. Therefore, the polynomial of f of x can be expressed as r of x into equal to f of x under modulo m of x. For example, so it is used in the advanced encrypt standard arithmetic in finite field of gf of 2 power 8 with irreducible polynomial m of x. You take it, consider the two polynomial f of x and g of x. If you add them, see x power sum separated as x power m, there is no only 1 x power 6, and then there is no x power 4, only 1 x power 4, and here only x square, and then rest of them becomes 0 because the polynomial is reduces to vanishes. Therefore, x plus x is 0, and then 1 plus 1 is 0. And then if you have a product, and simply the resultant will be like this. Already we expressed the product of f of x into g of x. Simply x power 6 into x power 7 is x power 13, x power 6 into x power 4 into x power 7 is x power 11, x power 4, x square into x power x square into x you have to do, it become x cube, and then x into, first you have to multiply with the x power 6 of all. So, x power 6 into x power 7 is x power 13, x power 6 into x power 6 is x power 7, x power 6 into 1 is x power 6. The first part will come. Second, x power 4 into x power 7 is x power 11, x power 4 into x is x power 5, x power 4 into 1 is x power 4, then x square into x power 2 is x power 9, x square into x is x cube, x square into 1 is x square. Next, x into x square, x power 7 is x power 8, x into x is x square, x into 1 is x, then 1 into x power 7 x 1. So, now add them. The x power 13 only one term, therefore, x power 11, x power 9, x power 8, x power 7 plus x power 7 0. So, these two become 0, then x power 5, and then x power 4, and then 1 x cube, then x square 0, and then x 0, then 1. So, this way we can multiply them. For the division algorithm, we apply it of this number x power 13, this number you take it divided by x power 8 into x power 4 plus x cube plus x plus 1. So, what happen? Multiply with first x power 5. So, x power 5 into x power 8 is x power 13, then x power 9, x power 8 plus x power 6, x power 5, then corresponding term add them. So, it becomes 0, here becomes 0, 0, 0, rest of them is x power 11 and x power 4 plus x cube, and then x power 11 multiply with what, x cube, so that this equation will come, and remainder is x power 7 plus x power 6 plus 1 only will come. So, that is the under modulo of this function. So, this way we can define the modulo corresponding to polynomial equation one divided by another in terms of the Galois field of 2 power 8 and apply in advanced encryption standard ideas. So, the residue class of x plus 1 under modulo m of x consists of all polynomial of a of x such that a of x is identically equal to x plus 1 under modulo of m of x, and equivalently the residue class of x plus 1 consists of all polynomial of a of x that satisfy the equality of a of x under modulo of m of x equal to x plus 1. So, to construct the finite field of g of 2 cube, we need to choose an irreducible polynomial of degree 3. So, there are only two such polynomials, one is x cube plus x square plus 1 and another one is x cube plus x plus 1. Using this later, table 5.3 shows that addition and multiplication in tables of Galois field of 2 cube. So, note that set of all tables has identical structure of those in table, and thence we have succeeded in finding a way to define the field of the order 2 cube. Now, read addition and multiplication of the table easily. For example, you have 100 plus 0 1 0 is corresponding 0 1 and 1. So, this is equivalent to the polynomial is here this is x square x and then constant, no constant, therefore, x square plus x. So, if you multiply that 100 into 0 1 0 is net value is 0 1 1, normal multiplication, and then binary bits you have to do. The resultant is x square into x is x cube and reduces to x plus 1 because the factor is the x cube plus x plus 1 can be written as x plus 1. So, it is equivalent to 0 1 1. Therefore, the polynomial arithmetic of under modulo x cube plus x plus 1. So, what happened? The corresponding binary bits to the polynomial equation 0 0 represent 0, 0 0 1 represent 1, 0 1 0 represent x, 0 1 1 represent x plus 1, 1 0 0 represent x square, 1 0 1 represent x square plus 1, 1 1 0 represent x square plus x, 1 represent x square plus x plus 1, and similarly for column wise you do the same. Now, you start to multiply 0 into 0 is 0, 0 into 1 x, x plus 1 x square, same thing will come, and then this part is also same will come under addition. So, it is not a multiplication. Now, 1 plus 0 is 1 plus 1 is 0, 1 plus x is 1 plus x, 1 plus x plus 1 is because 1 plus 1 is 0, therefore, x will come, 1 plus x square is x square plus 1, and here x square plus 1 plus 1 is x square plus x plus 1 will come, 1 plus x square plus x is x square plus x plus 1, and x square plus x plus 1 is 1 1 get cancelled, x square plus x. Similarly, for a third row x plus 1 is x plus 1, x plus 0 is x, x plus x is 0, x plus 1 is 1, x plus x square is x square plus x square plus 1 is equal to x square plus x plus 1, x square plus x plus x is x square, and x plus x square plus x 1 is x square plus 1. So, x plus 1 plus 0 is x plus 1, x plus 1 is x, x plus x is 0, therefore, 1, and then x plus 1 is 0. So, x square plus x plus 1, x square plus 1 plus x plus 1 is x square plus x square plus x plus x plus 1 is x square plus 1, x square plus x plus 1 is x square. Similarly, x square plus 0 is x square and then x square plus 1, x square plus x is x square plus x square plus x plus 1 is x square plus x plus 1, x square plus x square is 0 and x square plus x square plus 1 is 1, and then it becomes x, because x square is 0, x square plus this one is x plus 1. So, like that rest of them will come x square plus 1 this, x square plus 1 x square, and so on. We have same number come, it become addition is 0, rest of them will be reflected. So, x square plus x plus 1 is same, x square 1 get cancel, x square plus x, x get cancel, x square plus 1 get cancel means 0, the x plus x is 0, x square plus 1 plus x plus 1 is x square, x square plus x plus 1 is x plus 1, x square plus x plus 1 plus x square plus 1 is x, x square plus x plus 1 plus x square plus x is 1, and then it becomes 0. So, this way we can do the table. For multiplication, do that, and the same process of the resultant already we explained, and do the process of multiplication, so that we have a table. For example, for first row is easy, for first column also easy, second is 1 into 1 is 1, 1 into x, 1 into this same, because 1 is multiplying. Similarly, for this also same, because 1. Now, think about this, x into x square, here x into x plus 1 is x square plus x into x square is what? X into x square is x cube, but x cube is equivalent to x plus 1. So, x cube is equivalent to x plus 1, because cube root of unity, and corresponding that we have to under modulo 3 it reduces to this, and x into x square plus 1. So, it becomes x cube plus 1. So, x cube plus 1 is nothing but x plus 1 plus 1. So, which is equal to x. So, this become 1. Sorry, here x, and then x 0, and then we have 1. 1 is a net value. And then next is x into x square plus x, which is equal to x cube plus x square. X cube is x plus 1 plus x square, and then the value comes. And similarly, x into x square plus x plus 1 is x square plus 1. So, the same way we can find the rest of them. Like that, simply multiply them and use this condition, so that we can get it the value of binary bits corresponding to a cube root. Now, we can apply into extended Euclidean algorithm for polynomial and calculate r suffix minus 1 of a f, that is which satisfy the calculate v suffix minus 1 of x equal to 1, w suffix minus 1 of x 0, which satisfy a of x equal to a of x into v suffix minus 1 plus b into w minus 1.